Hey everyone, so today I'm going to talk about managing game objects and entity systems and that kind of stuff. And so there are a lot of different ways that you can manage objects in your game, and I'm not going to go through all of the various different things, but briefly there's sort of what I want to call the inheritance. Good God. Maybe I can write competently. Inheritance model. So this is kind of popularized in the old days when object-oriented programming was a thing. So very briefly, you have some kind of like actor or game object, and then under that, you might have like a renderable or whatever, right? So you have different, not really components, but different like types of things. Here you might have like static or something, who knows? And then down here, you might have orc, or maybe this is animatable. That's probably better. So things like anim and so on, and it's this kind of model, and I think we all know why this is bad. Like the real issue happens. You have anim and static, and then maybe this, you have like some destructible thing or something over here. Maybe some static objects are destructible, right? And so maybe you'll have some object and it'll cause it to kind of like fall apart, and then all of a sudden, under here you're like, I have this golem and I want it to animate, but also I want it to be destructible, right? And then you're basically screwed. You're like, how do I make this happen? And you don't. You don't make that happen. Not easily. And so what ends up happening is each of these add sort of their own functionality. That's what these lines are going to represent. And then what happens is, more things need it, so you start pushing stuff up. And then you have this massive blob here. I don't know why I put an E there. You have this massive like blob class here. And that's generally what happens. And this is true in a lot of inheritance models for just anything. Not even just game objects. So the second model, and this one's very popular, this one's the one that I've used the most, is I'm going to call it the component model. This is very common. Unity uses this, right? So Unity has its game object here. I'll describe it at first. So here, all it is you're taking this concept of a game object as a container of things. You're just replacing inheritance with composition. So game object owns some set of components, and then under here, these components are like, this thing can render. It can, maybe here's where destructible works, right? Destructible. And so the big advantage here, and so on, is that you just piece things together, and a game object is represented by the components it has. That's what the behavior is. And so, you have a lot of, so Unity does this. Unreal, I'll put an asterisk, like it's moving towards that. There are some things that kind of have to be done in the inheritance model. They have both. They actually have some of this. Early versions of Unreal were very inheritance based, and still have legacies of that, right? You have a actor, and then under that you have, I'm trying to remember what they all are. There's pawn, right? Well, a pawn, and then under here there's character, a character, and so on, right? And then in Blueprint, you're meant to even inherit this to my whatever. So this, they still, and they also have components which I think they're on the actor level. So they have both, and you can kind of do both. And there's an advantage and disadvantage to that, right? The advantage is that you kind of do what you want to do. The disadvantage is that it's hard to know the right thing to do. One of the philosophies of programming that I really like that's come from, I think this one came from, I don't remember exactly where I heard this one. It's probably from the Pragmatic Programmer. A lot of this kind of advice comes from that, which is make it hard to do things that the system is not meant to do. Don't make it doesn't have to be impossible unless it's really against it, but you generally want to make it easy to do the right thing. And sometimes you want to enforce this is how things work. You want to create some kind of some kind of box that people kind of have to play in, and they can do sort of whatever they want inside of this box. But as soon as somebody is here, you question whether or not that's the right thing to do, and so on. In a way, that's the whole point of sort of private versus public. Some developers say, screw it, make everything public. But to me, it breaks this kind of stuff. It's like, you want to make it easy to do the right thing. You want to make it hard to do the wrong thing. That's my opinion anyway. So this is the second way. There's a third option, and this is, by the way that I have the most experience with. I've written, 4 or 5 component systems, all sort of different in different ways. And as I said, hybrids are also relatively common. On The Sims 4, for instance, we had more of this kind of model. I don't remember what they all were. There was script object, game object, and sim. And most things were either, I think, script object. I don't remember if game object or script object, which one was higher. But if I recall, I think it was, let me go back to green. I think it was script object, game object, sim. And I think components lived here, and things were either this or that. And sim still ended up being this massive thing. Anyway, third option, which is newer. I mean, it's not actually that new, but it's newer. Certainly not really popularized. And that's what a lot of people are calling the entity component system, which confuses the hell out of me. The system in my game, the system that I have in my game that manages all the game objects, I call the entity component system. It is not this model. It actually is very much this model. This is also often called ECS, and I will generally use ECS. So it's confusing to me personally because I have to change my thing. Most people call this a component model, or sometimes a game object component model. My sort of game objects in my own world are called entities. That's the name that I've chosen for them. So that's why I've always called it the entity component system. So for me, it was a little confusing. But these are different worlds. So the entity component system is its own thing. Here, you basically have some kind of manager. Manager. And so this manager class, I'm going to twist this so I'm not drawing as much of an angle. This manager class, sorry, it doesn't inherit from anything, has two major sort of spurs here. This first one are the... There's a bunch of ways to do it, but effectively you have entities which in turn have components. And then over here, you have systems. And there are a couple of really important rules So entities have no subclasses. Components have subclasses. You know, render and all this other stuff. Collision, whatever, right? Collision. Systems also have subclasses. So we might have the render system. We might have like the AI system and so on. And so we have all of these different things. So let's go back here to the front and talk about a couple of these things. So in the inheritance model, what we have is I've already shown some of the bad sides and some of these downsides, right? Like blob classes. How do we compose these? In this component model, what we have a bunch of issues here. So let's see. I'm going to erase some of this stuff so I have a little room. Now, some of the issues that we have here are classic annoying coupling issues. We have the code that deals with certain aspects of the game spread out all over the place. For example, let's take a typical AI entity in the world. What components is this entity going to have? It's probably going to have a way to render, renderable. It's going to have some form of transform. It's going to have some kind of AI component or two. Maybe some kind of physics component, right? Like they're going to have a bunch of this stuff and other gameplay components and things, but even just these, right? And so in your traditional system, and mine doesn't work like this. The last system I created doesn't work like this at all because I think it doesn't make sense to do this. I actually hate this model. But you basically have something that looks like, how do I want to do this? I think this is going to be easier if I just type in, I don't really have like a Notepad++ thing. So I will just create a new file. Come on. Let's go ahead and make it a... Oh man, it's trying to... I have ReSharper and it takes a while to boot up. There we go. Let's just create a random CVV file. Mostly because instead of writing all this crap out, it's going to be a lot easier for me to just type it. Come on, ReSharper, you can do it. There it goes. Okay, 125. So essentially you have something like, you have your like object manager class, which has some update function that might have some, delta time. And then in here, you will say for, it's just essentially pseudocode, for game object, object in, game objects or whatever, right? You loop through every game object. No. And you say p game object dot update. This is how Unity works. This is how Unreal works. And then in here you have, game object. So, game objects have an update. And they basically do the same thing where they say for, and then your components, might be an array or it might be a hash table. Doesn't really matter. Component star p comp in m. Components, I'm going to pretend it's an array for right now. Oh no, what happened? I apparently saved this somewhere. That'll be fun to find. And then for each component, it's, p comp dot update, right? This is how you, like I said, this is how Unity and everything else works, mostly. And then each component, individually, maybe you have renderable, update, float, delta time. And then in here, it's like, whatever this is going to do, right? This will do some kind of like, gather render data, add to scene, or whatever, right? Like this is going to do the actual update. And so every component looks like this. And there's a lot of terrible things about this. First of all, this whole thing is pretty massive, right? It's big O of n, or if we want to be, a little more sort of obvious about it, we say big O of G times C, right? Where G is equal to number of game objects and C is equal to number of, say, maximum, I guess, number of components. The worst case, how many components do you have in your game? 50? How many game objects do you have? And the average game object, how many components do they have? 5 to 10, depending on your game. Maybe 10? Call it 10. How many game objects do you want to have in your game? 100? Okay. So this loop executes 1,000 times. And that's maybe not a big deal. 1,000 is not huge, but this is probably not a small amount of work that's getting done. So what happens is probably, you have something that looks like this, where in here you have some, virtual update, and this is your update, right? So already we're going to have some issues just looking at this code, because now what we have is we have class renderable, from component. And of course, this guy's going to have this stuff. So we're overriding some virtual function, right? But then, of course, what if we have something else like name component or something. So what we have to do here is we have to do the same thing. Except now we just maybe have it do nothing. So let's walk through what this does. Right? This virtual call, what's going to happen is when this loop executes, it's going to say, okay, component.update. So it's going to go to the v table. It's going to look up what is the actual pointer to the function that I want to call. It's going to then call that function, which is going to have nothing in it. And then it's going to bail. It can't really optimize that out because it doesn't know at runtime, or it doesn't know at compile time what this type is, what this type is. It has no idea. So at runtime, it has to figure out, okay, what is this type? And it may optimize the actual function call away, but it still has to figure this stuff out. Virtual functions, for the most part, are hard to optimize for the compiler to optimize because it can't streamline it. It can't, it might try and sort in cache in case that function happens to be called a bunch of times, but most likely that's not going to happen. So you're blowing your data cache, your CPU cache every single iteration, every single time, right? Because probably you're not going to have 4, say, name components or 4 render components on a single game object. It's going to have 5 totally different components, so it's going to jump around to 5 different update functions. So your iCache, your instruction cache, is not going to be able to cache those functions. So cache prediction is going to fail. Plus they're virtual functions, so probably they're likely not, it can't do any cache prediction. Whereas if it knew the exact type of these things as it looped through, it could at least predict which function it is and just, be streaming that stuff. A lot of times cache is sort of this magical thing where if it can really predict, you have a prefetcher. So, even if you have these theoretical cache misses, if it's really streamlined, it'll sort of predict and keep filling in cache. And, you might go through an entire array or something without incurring the absolute stall of a cache miss. So there's performance issues. This is fine. This is one of the reasons why I've always said that Unity is really good at sort of indie games or smaller games and really isn't going to stand up to AAA. They're trying to, right? They're trying to change that with their they've implemented, and I don't know how live it is. I don't keep up with Unity as much, but they have their own ECS system now, which is trying to address some of these concerns, and they're trying to address some of the performance concerns. For this reason, they want to compete in that larger space. So how bad are all these virtual calls? Well, again, if you have a bunch of objects. That's not great. And you can get around this in some way. So Unreal does this. If you're familiar with Unreal, it has things like, what is it? It's like can ever tick or something like that. So somewhere in some initialization function or in the constructor, you say can ever tick equals false. And then somewhere it does some post update that says, okay, I'm not even going to put you in my list of things to update. So when it's looping through this, like there's some list of, I think you might be able to do it for actors too. I don't remember, but I think you can do it for actors. And so there's not even a list to be updated. So you get around a lot of these false updates. So it's an optimization that they do, which works really well. My own system does something somewhat similar. In my own system, I have a sort of mediocre hybrid between these two, where I have this model, but also I have systems. And so my rule is that components never tick, so there's no update function on game objects or components. I have a system that maintains weak pointers to every, so like I have a render system, it maintains weak pointers to every single renderable, and it churns through them and does the rendering. So only components that need to update incur the cost of updating. It's a similar model for solving the same problem. But I still suffer from all the cache miss issues that I said. I mean, all these virtual functions. If you see virtual functions in any kind of high performing system, like you're already screwed. A high performance system should have no virtual functions. And when I say high performance, I mean rendering. Except maybe the very top call, but you should not. I should never see a virtual render function anywhere in the project. Again, unless it's like the one render call at the very top of the chain, but like no individual object should have a render call that's virtual, and so on. Like that's just terrible for any high performing system, physics or whatever, anything, pathfinding. There should be no virtual function calls in there. It's just too slow. Medium performing systems, I think you can be really, really careful as long as you're careful and know where the performance bottlenecks are going to be. Virtual functions are okay. But like an update loop, a virtual update function is something to really consider. If it's supposed to be a really tight loop, you can't do it, I don't think. If it's like a big overarching, like, here are the 5 major components of my entire game, each of them has a virtual update, who cares? You're going to call it a few times, you're going to blow your cache anyway when you hit it, and that's one of the big things, who cares? For low performing systems, and I'm talking things like gameplay systems that are called once every half second or second or something, who gives a shit? You can make virtual functions, you can do all sorts of stuff. I guess my rule of thumb is, if I would generally be okay with it living in a scripting environment, like Lua or something, then, and C#, by the way, is not a scripting environment. I would not consider that a scripting environment for Unity, even though they call them scripts. So if I would be okay with it living in kind of like a scripting environment, or like these sort of low performing things or things like that, you can kind of go more virtual function crazy. Because being able to compose at runtime is great. Just, know your tools. Like, you could get around much of this if you don't need to know at runtime what it is. You can do things with templates or whatever, and that has their own downsides. Okay, so there's a lot of different... So there's a sort of motivation. This is what we're building up to, right? So there's a bunch of downsides to this. So then we go to the entity component system, and there are downsides to this. It's sort of a new way of thinking for some people. As far as I can tell... I've not done exhaustive research here, but from what I understand, Thief, I think specifically Thief the Dark Project. This is back, so this is not the newer ones. This is back in the, Looking Glass Studios. I think they even did a GDC talk, and it's not exactly like the sort of classic ECS architecture. And what I'm going to talk about is probably not classic ECS architecture. It's just a different way of thinking. As far as I can tell, and this was, mid-90s? So this has been around for a really long time. It's becoming popularized. This is going to be a slight tangent, but I'm going to go on it anyway. There's this whole sort of wave over here called, where do I want to put it? Over here, called data-oriented design. And this is not to be confused, or programming, right? Design or programming. This is not to be confused with data-driven design or data-driven architectures. Data-oriented versus data-driven are two different things, completely different things, and not always at odds with each other, but can sometimes even be at odds with each other. Data-driven design is creating systems that are configured through data, such that the data is really the thing that controls it. I'll give you an example. On The Sims 4, there were maybe a dozen or so, there were hundreds, even probably even thousands of interactions in that game. An interaction is a sim going and doing something, something on an object or on themselves or whatever. So a sim going and reading a book is an interaction. I think there were maybe 20 interactions that were in code. The vast majority of interactions were defined 100% in data. All of the commodities, all of the motives that you see, hunger, food, hunger, energy, fun, 0 of them were defined in code. It was all data. Data would configure all of it, the name, how much it decays, and so on. That is data-driven design. It's something that allows you as a programmer to build a system with a whole bunch of buttons and knobs and dials and things like that, hand it to a designer or even another programmer. But usually a designer, have them use some tool to configure the shit out of it and make it feel good so that you guys can, so you as a programmer don't have to be constantly writing a bunch of code. Unity and Unreal and really any modern game engine is going to support these, facilities out of the gate. The serialized field in Unity does this quite well. So it's ways that you can sort of expose things to designers or even yourself. It's a lot easier to go in there and tweak values in some table somewhere in some Excel sheet looking thing compared to, say, walking through the code and being like, let me change these 5 constants. So that's data-driven design, something that's been around forever and that everyone agrees on. Data-oriented design is its own thing. Data-oriented design says, instead of thinking about the code, which is what we do a lot in programming, we think about, what is code? How do I architect the code in such a way that the code can change and code. Data-oriented design says, screw the code. I don't care about the code. I care about the data. And it really talks about transformations. This is something I've said a lot, is that programming is the manipulation and organization of data. That's what programming is. That's all it is. So you have, some kind of magic that happens here, and you have some... That is not a strong arrow, but you get what I mean. Some kind of input that produces some kind of output. And if you've taken a data structures and algorithms class, this is a very common concept in just computer science in general, which is, with this algorithm, what does it describe the transformation? Like the classic sorting algorithm, it takes in some set and magic happens. And then there's some set prime where, set of 1 is less than or equal to, index 2 is less than or equal to, index 3, ... is less than or equal to index n. That's the sorting. That's sorting. That's how you define sorting. So anyway, what it does is it says, let's look at data. Let's pack all the data together. There's a bunch of techniques for this. Having arrays of structures versus structures of arrays. The structures of arrays tending to be, depending on what you're doing, they can be better. It's like you want to group the data, so like a transform, for instance. If you're constantly doing moving things around, let's say that you want to store a transform and it's X, Y, Z, and then you have an orientation and you have a scale, a 3D vector for a scale. Well, if you store them all in this big array of these structures of data, as you're going through, the cache is going to load each chunk like this, and maybe it can fit these 3. And what's going to happen is you're going to only use this much, and then this part gets thrown away. You're going to use this much, this part gets thrown away, and so on. And so the idea being that if you can say, oh, actually, let's just group all of the, positional data together, because we're always operating on that. Now you're utilizing all of your cache, and you get to minimize the number of cache misses. And it's all about like these kind of micro optimizations, and they are micro optimizations. The only reason why cache significantly affects the performance of a game is because you're doing large sets of data. Games work on large sets of data. And the biggest wins that I've gotten from data-oriented design architectures are those things. Let me go through physics and transform a shitload of these matrices or vectors or whatever. Like, great, load them all up in one big array, churn through them all in one go. That's going to be lightning fast compared to, like, I have to, game object dot transform dot matrix. Like, that's going to be super slow, especially if that's a virtual function. So I'm not going to go into the details of how data-oriented design and programming work. You can look up a bunch of stuff. Keep in mind that in programming, and really in anything in life, there are people who swear by particular philosophies and believe that they believe in silver bullets. And in programming, I think one big rule is that there are no silver bullets. There really aren't. And, there are people, famous people out there. Mike Acton is one of them who, if you want to learn about data-oriented design, I highly recommend. He did a talk at CPPCon. He did another one at GDC. I highly recommend. The CPPCon one, certainly you can just find, and the GDC one is probably long enough ago that you can find it in the vault trivially. Just search for his name, Mike Acton talk or something like that, and you'll see he has this talk that he gives, and he has some really compelling data for it. And he's absolutely right, and if he's a hardcore engine programmer and all that stuff. Here's my problem is that I think him and people like him go too deep into that side of things. Like in gameplay, a lot of times we're optimizing for developer time than runtime, like CPU runtime in many cases. Or else we wouldn't be using scripting languages at all. Everything would be in pure C or even assembly language. Though C arguably is high enough level while still allowing you to figure out what assembly code is going to be generated from it. So I think there are some people who I think adopt this as this is the only way to do it. And it's interesting because I read some of the articles on this stuff and I just fundamentally disagree with certain aspects of it. For example, pure data-oriented design is not one of the things that they say is sort of less code and easier to understand. And I very much disagree with that. And it's not even just because I'm not used to it. I mean, that's probably part of it. But a big part of it is that the reason why we created something like object-oriented programming, or a big motivation of it, is for ease of understanding and sort of encapsulating things together. And when you break that apart, it becomes trickier to understand how things happen. Classic example is, I think in one of the articles I read, it's all about raycasting, just defer them all to this one spot. And it's okay, great. So, but what you're doing is you're obfuscating where that specific raycast that's causing me a bug is going to happen. So it makes certain things sort of more difficult. The performance benefits are undeniable. They can be really good. But here's the thing. If, let's say we go back to this and we have these monolithic update functions here. Here. And does it matter if, say, this object manager, if I were to, let's just look at object manager. Let's say that I have, let's say that I do something like this. Let's say that I have class, I don't know, updatable. Maybe that's how you spell it. I mean, this is a very contrived example, a very sort of arbitrary example. Update, and this is a virtual function. So now I can have a big list of these things, and I don't care, right? Delta time equals 0. And so now here, maybe this guy is an updatable. And there's sort of a convenience of just having, choosing which updatables you want, right? Because I can say, you know, I want to skip an object manager. This game, for some reason, doesn't need an object manager. Maybe it's all UI. It's like a tool. So I don't even include the object manager. And so trivially, without any work, you just don't instantiate it and add it to your list of updatables. Because probably up here, you have some kind of like, you know, list of updatable pointers or something, right? You know, list, whatever, right? So there's a virtual function called, like, this is very, very anti-data-oriented design. Who cares? No matter, like, this is going to be a big update, whatever this updatable is. Like, that's what this is for. You're going to get cache misses anyway. You're going to get a cache miss because it's going to use a totally different set of data. This virtual function is going to cost you nothing measurable. Who gives a shit? So, like, I think you can go too far in any direction. So my big thing is, when you read about this kind of stuff, question everything, including me. Question this video. Question the things that I'm saying. I have my opinions. I'm going to go in a direction that I think makes sense to me, but may not bear fruit, right? I don't know. We're going to do some tests, and we're going to see what it looks like, but I may be wrong. You know, Mike Acton may be wrong. Anyone else that you read, any article that you read, anyone, they can all be wrong. We can be wrong, and it's fine. They can also both be right. You can have two different views, have them both be right. And I'll give you an example. Unreal, when I say virtual functions, I've pissed on virtual functions a lot, right? I've said virtual functions are bad. If you look at Unreal's code base, they have virtual functions everywhere. Just open actor, actor.h. Open actor.h, open character.h. Holy God, they have so many virtual functions. And yet they are undeniably a highly performant 3D, like, top-end AAA game engine. I know several AAA games actively using Unreal 4. And so clearly you could make a AAA game with an assload of virtual functions. There's virtual functions everywhere. Also, undeniably, or at least in my experience, Unreal, more so than, say, Unity, is such a moddable engine. I was trying to figure out, what was I trying to do? Oh, I was trying to get, I wanted 2 different keyboard inputs, if I recall, or I wanted a keyboard plus gamepad or something like that. Like, I wanted the keypad to be player 1 and gamepad to be player 2. I think that's what I was trying to do. And it's like, Unreal is just not set up for that. However, there's like a magical class that you can just sort of inject in, that you just override these functions and tweak it. And, you know, you just subclass this thing, override this method, inject your code, and off it goes. And it's like very easy to just hijack a lot of their stuff. There's a lot of times where I've said, oh, I wish I could hijack this functionality. And you look and it's like, oh, it's just a virtual function. Hold on, let me create my own version. It just does the same default behavior, except in this one overridden function, I do my thing. So Unreal is very easy to do that, whereas something like Unity is much harder to do that with. They're a much more closed system, for better or for worse. So, you know, you have that advantage, and you lose a lot of that advantage in some of these more strict systems. I think a lot of data-oriented design systems can be more fragile to change. If you need to change something significant, you're going to change. If you change the data footprint, you know, one of the assertions is you have to significantly change the algorithm just because the data footprint's changing, and that's not actually true. Especially if you have well-designed sort of data and algorithms operating on that data, you can deal with a lot of different things. My world file formats change all the time, and my systems are fairly capable of handling all that. So, I mean, certainly there are cases, but just by virtue of even the amount of data changing and how it's accessed can change a lot of performance stuff. So, anyway, I think that there's merits in it. And so one of the things in your typical ECS system, which is what we're going to work on, spoiler, is that you can do more data-oriented stuff. And in some of the strictest versions of this, you can really do a lot of hardcore data-oriented stuff. And there are so many different models of this. My God. So we're gonna like sort of ignore this for a little bit. I'll leave it up here. So all the different models of this. I mean, if you look up ECS systems and just Google for it, and you look at different people's different architectures for it, they're all different in some way. But there are a few core tenets, and some of those tenets I want to just lay out right now. That this is what I think, personally, defines an ECS. Also, if you look around, you'll realize that it's not super defined either. But to me, here are the main things that separate it. And this part I'm stealing from a talk by Tim, I forget his last name. He's the lead gameplay programmer on Overwatch. And there's a GDC talk. It's probably not free. In fact, I know it's not free. I just watched it. They did it last year about their gameplay architecture. And I found the first half of it really fascinating. The second half was also interesting. Though it was more like, here's how we did it for netcode and some of the things that we got. So it was a little more sort of network focused, which I care less about. But the ECS stuff was super fascinating. And so we're going to talk a little bit about this. But anyway, I think he really defined these two features. To me, these two statements define an ECS system. And maybe three. I'll probably do three. Components have no functionality. They have no functionality whatsoever. Systems have no state. Those, to me, are the two kind of major tenets. There's sort of a third, which is sometimes followed. It's not always followed. I may or may not follow it. I'm sort of leaning towards not exactly following it. But it's at least worth mentioning, which is that entities themselves are basically IDs. So, why are you doing this to me? There we go. Entities are, I'm trying to think of a good way to put it. I don't want to say trivial because that's a loaded term. I'm going to say entities are essentially IDs. In pure ECS systems, I'll do it in blue. In pure ECS systems, entity looks like this, right? It's like type def, you know, unsigned int, you know, entity. Like in pure ECS systems, this is an entity. And in fact, in some systems that I've read about, which I don't know how many of them are actually in use, entity is an index into some array somewhere. But we have a lot of problems with that, and I'll talk about that. This, to me, these are the main things, right? This is it. Okay, so I think that's it for this video. It's getting kind of long. So what I want to do is, I'll stop it here, and the next video will go into more detail on ECS and some of the big questions on how we organize it and what it actually is. So I'll drop some more diagrams and things like that, and we'll start figuring out some of the skeletal work. I don't know if we'll get to that next video, but that's the goal. And then after that, we'll start implementing some stuff and doing some tests and things like that. So we'll see kind of what this looks like. So that's it. I hope you enjoyed the video, and let me know if you have any questions, as always, and I'll see you next time.